Hi, class. This is your chemistry notes for Monday, January 11th. We're going to continue on talking about the periodic table, and today we're talking about trends. So what I want you to do is make sure you have handy the periodic table that we started working with last week, the blank one. On the one side, we had started putting in information like the groups and the periods and the different types. We had transition elements, we had halogens, etc. We're going to fill out the back side of that today. What I do want you to do, though, is on that back side of your blank one, I still want you to put the period numbers on the left, the 1, 2, 3, 4, 5, 6, 7, to denote the period numbers, those rows. And on the top, using Roman numerals, use the 1, 2, 3, 4, 5, 6, 7, 8 to denote the columns that we're going to be doing. Now, if we would have had you guys in class with us, we would have done what we call a Mendeleev challenge. If you remember, Mendeleev was the man who we give credit to for coming up with the periodic table. And the main point of that challenge would be to help you to see that elements in the same group, that vertical, those columns on the periodic table, those have similar chemical and physical properties. So we'll see, like, for example, on the left, that first group, the alkali metals, they are metals, they're all solids, they're shiny, whereas if you go all the way to the right into the noble gases, they're all gases. And we can look at different things like that, reactivity, and lots of different things as we go through. But what I want you to see is if you go down that group, you'll just see some periodicity in any given property. They follow a pattern as you go down the group. Now, I had you color in your periodic table last week, your good version that has all the information on it. I had you put in these different colors, like the green, the yellow, the red. I'm sorry, the green, the yellow, the blue, to show us whether it was metal or a non-metal, or a metalloid. And we're going to use that same thing as well this week. Let's talk about our first trend. Our first trend is atomic diameter, or the atomic size. And really what we're talking about is how big the atom is. How big the atom is. And the trend we see here is that as you go down a group in the periodic table, as you go down, the atoms get larger. So what I want you to do is on your blank periodic table, I want you to put in on the left column there, put a little circle up at the top and make circles getting bigger and bigger and bigger until you get to the bottom, number 7. I also want you to then put in the left margin there next to the period numbers, put the atoms get larger as you go down a group. Larger as you go down that group. So which brings us back to the question, well, why are the atoms getting larger as you go down the group? Anybody like to guess? Well, I'll tell you here, it's because there are more energy levels for the electrons to fill. When we did our bubble charts before, we saw that we had a 1s level, and then we had a 2s level, and then a 2p, a 3s, a 3p. We kept adding more levels. Well, as you add more levels of electrons, think about those, you're adding more layers to your onion, if you will. Our onion's going to get bigger and bigger and bigger. So that's why our atom gets bigger as you go down in the periodic table. So I want you to write that as well on your blank version of the periodic table. Put by larger down as a group. Also put because more energy levels for the electrons to fill. So I want you to put, we're going to have the circles to give you a visual, and then have the labels, they get larger as you go down a group. And why? Because there's more electron levels to fill, more energy levels to fill. Now, there's still more of a trend with the atomic diameter. And the other one that we see is that atoms get smaller as you go across a period. Atoms get smaller as you go across a period. So back on our blank version of the periodic table, I want you to do this. I did it in period 3 just because it was easy. But you have the bigger atom at the left, and then circles get smaller and smaller and smaller as you go to the right, as you go across the periodic table. So in addition to drawing the circles, I want you to put that they get smaller across the period. Now, if I go too fast while I'm doing these, describing what I want you to do, please just hit pause in the video. And then when you're finished writing in or drawing in the things, then please continue on. I don't want you to worry about trying to keep up. I just don't want the video to be too long. So you have a trend. They get larger as you go down. They get smaller as you go across. So like before, why are they getting smaller as you go across? Well, if we think about that a little bit more, you think the nucleus is getting bigger, we have more positive protons in there. And the more positive protons, the more they can pull on those electrons. So if you want to think about it as if you have more protons, they're pulling those electrons closer. It's pulling them closer. There's a stronger strength to pull them closer. So that is why we see atoms get smaller as you go across a period. So I also want you to put that little piece of note on the back of your blank periodic table. Underneath where it says smaller across a period, I want you to put because the nucleus pulls harder on the electrons. More positive, you have more protons, more positive charges, it's going to pull harder on those electrons. So let me ask you a question this way. If I showed you a periodic table here, or at least a blank kind of version, and I got the trends there of the atomic sizes, where would we find the largest atoms? Well, hopefully it's pretty obvious based on those arrows, but the largest atom is going to be at the bottom, and it's also going to be on the left, right? Because our arrow says they get bigger as you go down, and the arrow says they get smaller as you go to the right. So our largest atom is going to be down on the left. Now, you can get many different versions of the periodic table, like the one that we have that gave you and we've been using for this class, but you can also have views of it here like this, where instead of having all the other information in there, we have the element, and then we have little circles to give you a visual on the atomic diameter, and the number inside there tells you how big that atom is. So the layout and the ordering is still the same as our normal periodic table. Just here, instead of highlighting mass like we do in our normal version of the periodic table, here we're trying to highlight atomic diameter. For trend number 2, we're going to talk about valence electrons. If you remember what valence electrons are, these are the electrons that you find in the outermost energy level. And they're important because they're the ones that are used in bonding. The inside electrons aren't available for bonding. Think about it, they're inside, they're being hidden. It's only the ones on the outside, on that outermost energy level, that are available for bonding. So hopefully it makes sense. They're the ones that control what's going to happen. Now, our group number tells us the number of valence electrons. Now, you know, my note there, it only works for groups that are in an A part of the periodic table. The B part of the periodic table was that middle part here. So that's why we're not going to, that trend doesn't necessarily fit there. But if we look at the A part, and you see at the top of my screen, let me see if I go back and do that again. You see at the top of the screen there, the 1E, the 2E, the 3E, those are all showing at the top of each group. That tells you how many valence electrons each group has. And this is real easy. The group number is the same as the number of valence electrons. One of the niceties of how we've chosen to create and lay out our periodic table. So on your good version of the periodic table, I want you to put that information as well. Just this part here. Put the 1 electron, 2 electrons up at the top of the above your period numbers on your good version of the periodic table. Just want to help you because it's very important. We're going to be using these valence electrons a lot. I want you to have a good visual for that. Okay. Now, we do have an exception here. If you look at group 8A, group 8A, if you look at that first one, that helium is our exception. It only has 2 valence electrons. It's because it's in that first row, that first period. And when we were doing our bubble charts, remember, our first energy level only had 2 electrons. It just had an s orbital, so it only had 2 electrons. So that's why we have helium being all the way on the right. So even though it's in group 8, it doesn't have the 8 valence electrons. It has 2. But all the other ones work. So helium is our exception for this particular part of our properties. Helium, again, only has 2 valence electrons. Now, remember, we're talking about valence electrons. They only use in bonding. And again, the group number tells you the number of valence electrons, except for helium. So let's look at some examples. If we look at potassium, I want you to see if you find potassium in your periodic table, you're going to see it's in column 1, group 1. It has 1 valence electron. If you look up sulfur in your periodic table, you can see it's in group 6. So how many valence electrons? 6. Helium is in group 8. That's our exception. Helium only has 2 valence electrons. Oxygen is in group 6. It's going to have 6 valence electrons. Argon in group 8. it's going to have 8 valence electrons. Strontium in group 2 has 2 valence electrons, and tin in group 4 has 4 valence electrons. So this is a pretty easy trend that I want you to be able to see. The group number tells you your number of valence electrons, the number of electrons in your outer shell. With helium being our exception, it just has 2. Our third trend we want to talk about is ion formation. So when the atoms are going to form an ion when they're trying to bond to each other, like sodium and chlorine bonding together to make sodium chloride, salt, how do those ions form? Well, first let's talk about the metals. Remember, we had them colored in green in our periodic table, and these were tended to be on the bottom and on the left. These form what we call cations, and I think we talked about those before. Think of that T there in the cations. If it's written in lowercase, that T almost looks like a plus sign, so hopefully that T helps you remember that cations are positive. Well, how do we get a positive ion? Remember that we can't change the protons. All we can do is change the electrons. So if we're going to get positive, that means we have less electrons than we have protons. That means metals are going to give away their electrons. They're going to give away their valence electrons. Non-metals, right? We color those in yellow, and we call those anions. They're negative. Think of that an, the N and the an, that prefix. That N stands for negative. And these are formed when the atoms gain electrons. Again, we can't change the protons. All we can do is change the electrons. How do we make something negative? We add more negative particles. We add more negative electrons. So let's put this on the blank part of the blank version of the periodic table we've been working on today. So on the left-hand side near the top, I want you to put gives electrons and they're positive. The right-hand side near the top, I want you to put takes electrons and makes them negative. Okay, and we'll talk about those a little bit more definitely in the next few days. And our next trend that we're going to talk about is reactivity. Trend 4 is reactivity. Now, as we go on to talk about this, I want to talk about, do a reminder of what we talked about last week about our groups. I remember we called group 1A, or alkali metals, very, very reactive. Our group 2 metals were still reactive, but not quite as reactive as our alkali metals in group 1. Our group 7 there are very reactive, most reactive nonmetals. And then group 8 are noble gases. Remember, they're inert. They don't react at all. So here is some information about reactivity that we can see on our periodic table. So again, on the blank periodic table that we've been filling out today, I want you to put alkali metals on in the left column there. And I want you to put that they're the most reactive. And similarly, on the next column, put their alkaline earth metals. They're not quite as reactive, so we'll just call them reactive. When we get into our transition metals here, they're transitioning from metallic to non-metallic properties. Right? And our rare earth ones then are the ones on the bottom. Now, the next thing I want you to see, especially when I'm talking about rare earth metals, let's look at our periodic table. When you look at your periodic table, in the bottom left there in period 6 and 7, notice that the first 3 elements are 55, 56, 57, 87, 88, 89. But if you look at the 4th element, the one in the next one over, notice it jumps from 57 to 72. And if we go down to period 7, it jumps from 89 to 104. Well, what's up with that? What I want you to see here, I can try and kind of draw this way. If you look at the bottom, our rare earths, what I'm trying to do with that symbol I just put in there is trying to say, hey, we took out those elements that were between 57 and 72, between 89 and 104. We pulled them out and we put them at the bottom of the periodic table. Those are our rare earth elements. And if you look at those, you're going to see exactly they fill up the missing spaces. It starts with 58. Well, that's the next element after the 57 that we see in period 7. And it goes all the way up to 71. That fills in the last missing one in period 6. It fills in the last missing one in period 6. So you see we kind of just took this little group out and pulled it to the bottom. We did that for a couple reasons, and I'll talk to you more about that later, but one of the easiest ones to see is if we would have put them in there, our periodic table would have gotten really, really wide, and it would have just been unwieldy to put on a piece of paper. But we do have to understand what's going on here, and I'll tell you kind of ahead of time, this is where we're filling up our F orbitals, and we'll see that more and understand that more in a little bit. This is what the periodic table should look like if we would have put the rare earth elements into it. You see it makes it really wide, and we've got yet another gap kind of in the middle for most of our columns. It just makes it a little bit harder to use. So we, instead of using this version, we're much more comfortable just taking those 2 rows out and sticking them there at the bottom. It still gives us most of the information that we need at an easy glance. Okay. So back to our groups that we want to know. Remember, we talked about our alkalis, alkali metals, or alkaline earth metals, groups 1 and 2, and then our halogens and our noble gases, groups 7 and 8. And in between there, we had the transition metals and the rare earth metals. Right. So this is where we put those onto our, let's put the rest of these labels onto our blank version of the periodic table. The transition metals there in the middle, the rare earth ones on the bottom. Group 7 is our halogens. Remember, they're the most reactive non-metals. Alkali metals, group 1, alkali metals are the most reactive metals. Halogens, group 7, most reactive non-metals. And then group 8, let's put our label on there for the noble gases. And what do we know about them? They're inert. They don't react at all. So back to our trend on reactivity. Let's talk about the metals first. Metals become more reactive as you go down a group. So if we look at group 1, for example, what you'll see here, and I'm trying to figure out how I want to put this in here. I want you to put a little, see how I put the little green part jumping in there. Metals get more reactive as you go down a group. So that applies to group 1, group 2, any of the groups there that we see for our metals. They get more reactive as you go down a group. So what would be the most reactive metal we have? Well, we saw that the alkali metals, group 1, were the most reactive metals. So what's the most reactive in that group? It's the one at the bottom. So that would be francium. Now, nonmetals, where we saw earlier, they tend to be opposite of metals in many, many ways. And this is another one of them. They become more reactive as you go up the group. So metals get more reactive as you go down. Nonmetals get more reactive as you go up. As you go up. Let's put that on our blank version of our periodic table. Yeah, it's getting pretty crowded on this one. Let's put more reactive as you go up in a group, and use the same coloring you did for your nonmetals, so we can help you distinguish that, and also have it going the other way, so you're reading as you go up as opposed to going down like you did the metals. So more nonmetals become more reactive. So what's our most reactive nonmetal? Well, we said earlier that our most reactive nonmetals are in group 7, or halogens. If they become more reactive as you go up, then it's going to be the one at the top that's the most reactive, and that's going to be fluorine. Will be our most non-reactive nonmetal. So the question I'm going to ask you here is, why not helium? Why wouldn't helium be our most reactive nonmetal? It's at the top of the periodic table. But if you remember, group 8, those are our noble gases. Those are inert. They don't react at all. And we'll find out a little bit more why as we continue on in this unit. It's not going to be helium because it's inert. Our most reactive nonmetals are not at the far right. Like our most reactive nonmetals are at the far left. But our most reactive nonmetals are one row in, one group in from that. We'll talk about the demos here, reactive metals here later in the week. Hope that can make sense to you guys. I know there's a lot here. If you need to pause and repeat the video a couple times, make sure you get your blank version of periodic table updated. It'll be a great study guide as we finish up our unit here. All right, guys, have a good one. Take care. Bye-bye.